CLI and a cross-platform IDE for C and C++. Download now.
Hello everyone and welcome to Zero Cost Abstractions in Large Systems. Today we are going to look at some hardcore high performance C++ software architecture hidden inside a place you might not expect, the Java virtual machine. Before we dive into the code, a quick bit about me. I am Shubhankar Gambhir. I like to think of myself as a C++ developer who makes life easier for Java developers. I work at Azure Systems where I focus on performance and runtime behavior in the JVM. A lot of my work involves digging into how these systems behave under real workloads. I build small C++ prototypes to explore trade-offs, validate optimizations, etc. Especially looking at how components like garbage collectors are integrated into runtime. This talk dives into the OpenJDK codebase to see what zero cost really requires at an industrial scale. We are going to explore how C++ abstractions are used in practice, and most importantly, how to use heavy template metaprogramming to handle dynamic runtime dependent behavior without ever paying the price of virtual function call. Because I spend my days writing C++ for a Java engine, I want to invite you to look at Java through that exact same lens. To understand the extreme C++ metaprogramming we are about to explore, we first need to shift our mindset and look at Java strictly from systems programming perspective. To an end user, Java is a high-level managed language, but Java applications runs on JVM, and OpenJDK's JVM hotspot is just a massive, highly optimized multi-threaded C++ application. So, under the hood, OpenJDK's JVM is C++. But the single biggest fundamental difference is writing C++ and writing Java is memory management. In C++, we explicitly dictate object lifetimes. We use new, delete, or standard unique pointer. In Java, the user allocates memory, but a C++ engine is solely responsible for finding and reclaiming that memory when it is no longer needed. Garbage collection in JVM is implemented through different algorithms. At a high level, one way to think about memory management is reference counting, similar to shared pointer in C++. But that's not how the JVM works, but it gives us a useful starting point. In practice, the JVM uses tracing collectors. These start from a set of root references and discover all reachable objects, essentially building a graph of what's still in use. You can think of it like drawing a map of all the roads that are still connected. Now, traditionally, this was done in the stop the world phases, where the application was paused time to time to rebuild that map. To improve performance, generational collectors were introduced. They are based on the observation that most objects die young, so the heap is divided by age and younger objects are collected more frequently. This allows older generation to be collected less often based on heuristics, but it requires barriers to track references across generation. As a further optimization, concurrent collectors were introduced. Instead of pausing the application, they try to build and maintain that map while the program is still running. So you are effectively drawing those roads while the roads themselves are changing. And barriers are what help keep track of those changes. Historically, ensuring these barriers executed correctly was an architectural nightmare. Look at this legacy C++ code on the right. The C++ developers working on the JVM runtime had to manually execute these GC barriers imperatively every time they touched an object. It was a tangled mess of if-else checks scattered across hundreds of thousands of lines of runtime code. This imperative design resulted in extreme tight coupling. So, if you want to introduce a new state of the art garbage collector like ZGC, You had to manually hunt down every pointer, have every pointer right in the code base, and patch it to support your new GC. And if you work in core runtime, you need to know which tracking logic needs to be called for which collector every time you add a new memory access. It was completely unmaintainable. To fix this, the OpenJDK team introduced JEP 304, which is Java Enhancement Proposal 304. The goal was simple: decouple the JVM execution engine from the garbage collectors. Core runtime engineers shouldn't worry about which tracking logic needs to be called for which GC. Adding a new GC should be just be a matter of fulfilling a contract into the build without ever touching the core execution engine. To do this, they needed to transition from that imperative manually checked spaghetti code into a clean declarative model. But whenever you introduce a clean abstraction layer in C++, especially for something that executes billions of times in a second, like memory access, you face a huge risk, destroying your performance. This is where the brilliance of their C++ design comes in. They introduced a strict architectural split. On the front end, we have a declarative access API. C++ developers in the JVM no longer write imperative tracking logic. They just use a decorated template API to declare their intent. For example, I am doing a volatile write into the Java heap. Whereas on the back end, we have the GC interface, which is barrier set. It provides a standardized contract completely isolated from the rest of the JVM, where each garbage collector implements its own tracking logic. And bridging the two is the Access internal pipeline, a massive C++ metaprogramming engine that takes that declarative intent, safely crosses the runtime boundary, and wires it directly to the active GC. For the rest of this presentation, we are going to explore this entire architecture, starting at the front end API, traversing the 5 steps of the internal pipeline, and finally seeing how the GC backend plugins with the zero overlay. But before we look into how this pipeline routes memory operation, we need to understand exactly what we are routing. What is the payload? If you are a C++ developer, you are used to raw pointers like int star, void star, my class star. In JVM, C++ code base, a pointer to a managed Java object is called an OOP, which stands for ordinary object pointer. By default, on modern hardware, an OOP is just a standard 64-bit C++ pointer. But 64-bit pointers create a massive performance bottleneck in Java. Why? Because Java applications are famously object heavy. If every pointer is 64-bit, 8 bytes, your memory footprint explodes. Worse, you can only fit half as many pointers into a CPU cache line compared to 32-bit pointers. That means double the cache misses. And you bottleneck hard on memory bandwidth. To fix this, JVM uses a brilliant trick called compressed loop, or in the C++ code, narrow loop. If your Java heap is under 32 GB, the JVM doesn't store absolute memory address. Instead, it stores a 32-bit offset from the base of the heap. Because Java objects are 8-byte aligned, the CPU just takes that 32-bit integer, shifts it left by 3 bits, adds it to the heap base, and boom, you have your 64-bit address. But here is the catch. For us as C++ developers, the hardware CPU does not natively understand a narrow. To the CPU, it is just a 32-bit integer. It is entirely the responsibility of the C++ access pipeline to transparently inject the shift and add assembly instructions every time it reads or writes one of these pointers. So our C++ code base has to juggle 64-bit oops, 32-bit narrow oops, and draw primitives like int and float. And we have to do it safely. Let's look at the front door of our new declarative access API to see how it handles this. This is the access class. It is the public face of the pipeline, and it is the only way JVM developers are allowed to touch memory. Notice how deliberate this API design is. It splits the operation across two different axes. First, the addressing mode. We have store, a direct pointer write, and store at. A write into a base object plus an offset. Store at is critical because it always implies a heap access. You are bypassing and you are passing an OOP base, a managed object. Even if you are just writing a primitive int into that object, the garbage collector needs to know about it because GC might be moving that base object around in memory while you are trying to write to it. Second is the data domain. We explicitly separate the primitive store from OOP store. As a C++ developer, you might look at this and ask why not just use a single generic store T and let the compiler deduce the type. The answer is that C++ is dangerously permissive with implicit conversions. In the older version of JVM, it was notoriously easy to accidentally cast an object pointer to void star to do a generic memory write and silently bypass the garbage collector's reference tracking logic. This leads to a catastrophic heap corruption. By forcing the developer to physically type the function name OOP store, the API establishes a hard semantic boundary. We force the human to declare their intent and look at what the API does with that intent. In the bottom function, it takes the developer intent and automatically injects the internal value as decorator into the bitmaps. From here, both paths funnel directly into the access internal pipeline, carrying those strict compiler verified tags with them. But just declaring this as an object isn't enough. The runtime needs to know how to write it. Does it need a memory fence? Is it in the heap? Normally, in C++, you would pass these as Boolean arguments to a function. Store address value with true or false as far as options. But evaluating those ifs at runtime inside a hot loop is too slow. Instead, Hotspot passes configuration metadata as non-type template parameter called decorators. Under the hood, a decorator set is just a 64-bit integer mask. You can see the categories here. We have memory ordering decorators that map exactly to C++ living hardware atomics, like MO sequential cast. We have location decorators like in heap versus in native. We have optimization hints like is destination uninitialized, is not null. Notice that orthogonal decorators like memory order release and in heap are mixed in the same bit mask. The pipeline separates these two concerns later. Look at the code snippet on the bottom left. The pipeline evaluates these bits using standard integral constraint. This is the secret sauce because these bitwise checks are resolved by compiler. They turn into strict compile time booleans. This pipeline uses this with standard enable if to perfectly route logic, trigger SFI NAE, and aggressively prune dead branches from final assembly. With this vocabulary established, let's trace an actual memory write through the 5 steps of internal pipeline. So the developer has typed access with the decorators in heap and MO relaxed, OOP store address object. The public API has captured the intent. Now we hand it off to the internal pipeline. This is the meta programming engine that wires the intent to the correct GC implementation. Here is the architectural roadmap of the pipeline. It's designed as a funnel and it operates in 3 distinct phases. Phase 1 is 2 steps. It is all about normalization and state injection. The compiler is gathering data It looks at your inputs, strips away C++ type noise to stop template load, and injects internal state tags so the backend knows what it's dealing. Phase 2 is a compile time short circuit. The compiler looks at the data it just gathered and asks, do I actually need the garbage collector? If the answer is no, it bypasses the rest of the pipeline and wires directly to the ROM access. Phase 3 is the runtime bridge. If we do need the GC, we have to cross the compile time templates. If we have to cross from compile time templates into runtime JVM state. We do this using self-patching thumbs. Let's start at the top of the phase 1. Step 1 is the front door. It acts as our bouncer and our translator. It has three main responsibilities: type normalization, semantic, defaults, and tagging access. First, we have to deal with the reality of C++ template mode. In C++, int star, const int star, and volatile int star are completely different types. If we pass these raw types down a massive 5-step pipeline, the compiler will instantiate three identical massive copies of the garbage collector tracking logic. It destroys the compile times and increases the binary size. To fix this, step 1 uses standard decay. It forcibly strips away const, volatile, and differences, collapsing them all into one clean path. But we have a second load problem specific to the JVM. Internally, Hotspot has a whole soup of object pointer derivation: instance OOP, object array OOP, OOP description, JObject, and so on. We don't want to generate separate GC barrier for all of those. So the pipeline uses OOP or narrow OOP meta function shown on the right to aggressively canonicalize them. Remember, in the public API, when the user called OOP store, they made a contract with the compiler. They swore that they are passing an object. This meta function enforces that contract. If you look at the code, if the type is explicitly a 32-bit narrow OOP, it preserves it. For literally anything else, it forces the type to become a standard canonical OOP. And here is the brilliant safety catch. What if the developer lied? What if they accidentally passed a double star into OOP store? Because this meta function attempts an implicit conversion to OOP, an invalid type will fail that conversion. The compile will break immediately, exactly as desired. As a result, the downstream code is completely shielded. It only ever has to deal with pure sanitized types, bare primitives, canonical OOPs, or narrow OOPs. But wait, if we just use standard decay to strip the volatile keyword away from a pointer, didn't we just lose the developer's memory ordering intent? This is where step 1 does some beautiful translation. Look at this decorator fix-up ternary operator. Before it decays the pointer, it uses type traits to ask standard is volatile p. So if the C++ pointer is volatile and the developer didn't provide any explicit memory ordering decorator, this logic dynamically injects the JVM's MO relaxed decorator into the bit mask. It translates a C++ language keyword directly into the JVM pipeline semantics with zero runtime cost. Finally, let's look at how step 1 tags access. It is very important to note that this specific tagging only happens for the store at variant. Look at the signature. We are passing an OOP base and an offset because we are explicitly writing to a managed Java object on the heap. The pipeline knows immediately that it needs to prepare for compression. It checks if hash decorator internal value is OOP. If true, it injects the internal convert compressed loop decorator right here in step 1. It is arming the pipeline for compression. Now notice the routing. Because storage gives us this context up front, It completely skips step 2, which is type reduction, and jumps directly to step 3, which is pre-runtime dispatch. If this were a regular store, step 1 won't have enough context to tag it safely. It would have to pass the access down to step 2 so the compiler could analyze the destination address type. So to summarize step 1, we verify the input, we translate volatile to MO relaxed, and we decay the types to stop template load, and we tag the object for compression. Now we hand those clean decayed types to step 2. Step 2 is called type reduction for a very specific reason. It forces the permissive C++ types from step 1 into a strict physically realistic bounds. It has two main jobs: strict type reduction for primitives and resolving the complex loop problem. Let's talk about that strict type reduction first. Back in step 1, the signature was store T star address T type value. That is dangerous. We pass that all the way down, the C++ compiler might allow a developer to implicitly cast an int to a float star or accidentally store an oop into an int star address. To stop this, the top row of this matrix, the generic primitive path, enforces strict type reduction. It changes the signature to store reduced types, which is T star address T type value. By forcing the pointer type and the value type to use the exact same template parameter T, any attempt to mix types will cause a compilation failure immediately. But what about the rest of the matrix? When we are storing managed loops, we have to deal with the physical reality of JVM memory. We might be storing a 64-bit OOP into a 32-bit narrow OOP star address or into an ambiguous heap word star address. Heap word star is just a pointer to the Java heap. We don't know at compile time whether it is an OOP or a narrow OOP. That's why it is ambiguous. So how do we resolve that? We solve this using C++ function overloads mapped to that matrix. Look at the top snippet. This is the strict type reduction for primitives, T star address T type n. It covers both primitives as well as standard loops, none of which needs to be tagged. It passes the types straight through unmodified. Now look at the middle block. If the C++ type system tells us the address is explicitly a narrow loop star, the compiler knows compressed loops will be used in runtime. It injects the internal runtime use compressed loops tag. This tag tells the downstream pipeline, do not bother checking the runtime flags. I'm statically guaranteeing that you are storing to a narrow loop in runtime. It eliminates the runtime branch entirely. Finally, look at the bottom block. If the address is a heap word star, it is a pointer to heap memory. The compiler has no idea if this JVM booted with compressed loop enabled. So it injects the potential tag internal convert compressed loop, but intentionally omits the confirm runtime tag. It safely defers the decision to the runtime pipeline. Step 2 resolves the overloads, enforces the type reduction, injects the final compression state into a decorator bit mask, and passes it to the phase 2, which is step 3. We are now holding a fully populated, heavily tagged decorator bit mask. Step 3 acts as the router. Its entire job is to ask, can we avoid the garbage collector? It does this using SFI via standard enable if. Look at the first function, is hardwired primitive. It simply checks if the internal value is OOP tag is missing. If it is missing, it is just an integer or a float. That is, it's a primitive. The GC doesn't care. The enable if logic automatically promotes the call by injecting the as raw decorator and routes it directly to the hardware. If it is an OOP and the developer didn't explicitly ask for a raw bypass, it routes to the runtime dispatch, the slow part to the GC. But what if we were routed to the raw hardware? We still have one last trick, which is for pointer compression. Look at the CAN hardware roster. It evaluates the standard integral constants to see if step 2 statically proved that we will or we will not be dealing with narrow star. If so, it routes to the top store function, which is a direct branchless dump to a hardware layer. But if step 2 left it ambiguous, the heap word star case, SFI NAE routes it to the bottom function, and here finally we see a runtime check if use compressed loops. We check the runtime flag, resolve the ambiguity, and inject the final decorator and recurse back into the pipeline. And that brings us to the end of static pipeline. Step 3 has evaluated all our rules. If we were lucky and the compiler could prove it was safe, we got routed straight to the raw access barrier. If we needed the GC, we got routed down to step 4. Please note one brilliant architectural detail here. That is, for raw access, the store at variant actually degrades and calls store. If you if you see here, if we had store at, then we will actually call store here with the actual address. Why? Because the only reason store at exists is to give the garbage collector the base loop so it can update its tracking metadata. If we are doing a raw bypass and we don't need to maintain that loop, and we don't need to maintain that loop base anymore, the pipeline simply computes the absolute memory address, base plus offset, and passes that raw pointer down, keeping the backend interface as minimal as possible. Next, let's look at what actually happens when we hit that raw store. So step 3 just hardwired our access and routed us to a raw access barrier. We have successfully bypassed the garbage collector. We are at the meta layer. But as C++ systems programmer, we know that touching bare metal in a multi-threaded engine requires strict discipline. First, we need to clear up a massive misconception. In the hotspot codebase, a raw access does not mean a blind, uncontrolled C-style pointer, right? Raw specifically means no garbage collector overhead. The access is strictly managed. The raw access barrier has three critical responsibilities. It must handle pointer compression, it must enforce strict hardware memory ordering, and it must execute the actual atomic assembly instruction. We use this for primitives like int of float, or for off heap memory where GC isn't watching, or when step 3 statically prove that tracking an object is logically unnecessary. Let's look at the first major responsibility of the backend, compression. We have a source value of type T and a type erased destination address. We need to reconcile them using standard C++ type tree. Heap hoop type. It is a destination. If you look at the top block, we need to determine the physical layout of the memory we are writing to. The pipeline checks the decorator if the compression tags are present. Needs hoop compresses true. When we then use standard conditional to define heap hoop type. If true, the destination is a 32-bit narrow. If false, it's a 64-bit hoop. Now comes the check, the must convert compressed hoop. If you look at the middle block, do we actually need to perform an encoding operation? We use standard is same to perform a logical AND check. Is the destination, which is the heap hoop type, a narrow hoop, and the source, which is the T type, and hoop. If both are true, must convert evaluates to true. This confirms we have a fat pointer source that needs to be squeezed into a narrow destination. Encoded type. This is the transformation. Finally, the bottom block. We should, what should the value look like after encoding? We use standard conditional again. If we determine that OOP heap OOP type conversion is needed, the encoded type becomes a 32-bit heap OOP type. Otherwise, for primitives or uncompressed pointers, it stays at T. This prepares the types so that in the next step the compiler knows what casts to generate. So we know we need to compress the pointer. How do we actually do that efficiently? This encode internal function is the workhorse. It uses SFI with enable if again to select the right implementation at compile time. First, let's look at the case 2, which is at the bottom, the no compression case. If must convert compressed loop is false, say we are storing an integer or a standard uncompressed pointer, the compiler selects the bottom function. It is a pure pass-through. It returns the value untouched. Crucially, the compiler inlines this. The function call disappears entirely, leaving just the raw value. Now let's look at the case 1, which is the top one here, where compression is required. We hit the top function here. This calls compressed loops encode, which emits the actual bit shifting and base pointer addition assembly instructions. But look closely at the optimization inside. That if the block in that if block, we have has decorators is not null. So if the developer told us back at the public API that the value is definitely not null, the compiler evaluates this check to true. If it then calls a specialized encode not null function, why does this matter? Because the standard compression requires a CPU branch. If value not null returns 0, else shift and add. By proving that the value is not null at compile time, we skip that if check in the runtime completely. Here is how it all comes together in OOP store workflow. We take the void store address and the high level OOP value. We use our meta function to define the encoded type, which is narrow OOP or standard OOP. Then we call our SFI encode function to physically compress the bits. Finally, we delegate to the generic store. Notice what happens on the last line. We pass the newly encoded value down because C++ templates infer types from their arguments. The generic store function now strictly knows exactly how many bytes it needs to write. And this is the final destination, the store internal function. This is where we will fulfill the final responsibility of memory ordering. We will again use SFI to map the high level decorators directly to the low level atomic hardware calls. If your decorator was MO sequentially consistent, the compiler generates exactly one function. It calls atomic release store fins, emitting a full hardware memory fins. If your decorator was MO relaxed, it calls atomic store, guaranteeing no word tearing, but allowing the CPU to reorder. And look at the critical cast inside those calls. Reinterpret cast volatile T star atlas. That T is the encoded type deduced in the last. Because T is perfectly resolved as either a 32-bit or 64-bit type, this reinterpret cast guarantees the C++ compiler emits the exact right instruction width. Now let's return to the pipeline. What happens if step 3 couldn't hardwire the access? What if the compiler realizes we are modifying the Java heap and therefore we must route this right to the garbage collector so it can track it? We have now reached phase 3, the runtime bridge. We immediately hit a massive architectural wall. Up to this point, our entire pipeline has been built on static C++ templates. Everything is resolved at compile time. But we don't know which garbage collector the user is going to run until they boot the JVM and pass a flag like use G1GC or use ZGC. Furthermore, if step 2 left our pointer compression ambiguous, we don't know if use compressed loops is enabled until runtime either. We have to evaluate these runtime flags. But if we put an if else check inside this pipeline, that check will execute billions of times a second. The CPU branch predictor will crash and performance will tank. We need a way to evaluate the runtime state exactly once and never pay the cost again. The solution to this paradox is step 4, the lazy resolution using a thumb. If you aren't familiar with the term, a thunk is a piece of code used to delay an evaluation. Here is how Hotspot uses it. Initial state: when the JVM boots, the access API sets up a static function pointer, but it doesn't point to the garbage collector yet. It points to a special setup function called store in it. On the first access, the very first time your application tries to write to a memory, it calls that pointer and hits store in it. The function pauses, looks at the JVM runtime flags, figures out exactly which GC template to use, and then crucially, it updates its own function pointer to point to that new template. Finally, it executes the write. On subsequent accesses, the next billion times you write to memory, store init is never called again. The code jumps directly to the highly optimized GC template. The only overhead is a single monomorphic indirect function call. It acts like a user space trampoline. Let's compare this to a standard C++ virtual function. A virtual function call has two layers of indirection. First, you do a memory read to fetch the correct function pointer out of the vtable, and second, you invoke that pointer. By using lazy resolution and self-patching thunk, we are completely getting rid of the vtable read overhead. We are left with just one indirect jump to the correct function pointer. Let's walk through the actual C++ code powering this dispatching. Look at the runtime dispatch struct on the left. Notice that it is templated on decorator set and the type T. This is critical. It means the compiler generates a unique function pointer for every single combination of decorators and type. Instead, inside this struct, we have three things: func t, which just abstracts the function pointer signature; store func, the actual static function pointer. This is the variable that gets dynamically patched at the runtime; store init, the resolver function that handles the patching on the first invocation. Now look at the bootstrapping box on the bottom right. To see how this starts, at startup, store function is assigned the memory address of store init. Because this is tied to a specific template instantiation, we get lazy evaluation for free. If a specific access type, like a store with as no keep alive decorator, is never actually executed by the application, we never pay the CPU cost of resolving its barrier. It just sits there pointing to the init function forever. Finally, look at the top right, the public interface. This is what the rest of the pipeline actually calls. It is designed to be as thin as possible. It simply calls store func address value. It blindly jumps to wherever that pointer tells it to go. By doing this, the total runtime overhead for bridging this massive template pipeline into a dynamic GC state is reduced to exactly one single indirect call instruction, a simple register based call at the assembly level. I want to briefly point out that step 4 actually maintains a separate path for store at operations. Why? Because store at preserves the base object pointer and the offset rather than just passing a raw calculated memory address. I'm repeating this again because it is critical. As the advanced garbage collectors desperately need to know the base object address to apply this metadata changing. So the pipeline faithfully carries both addressing nodes across the runtime bridge. So the first time we write to memory, the thunk calls store init. Inside store init, it delegates to step 5, the barrier resolution. The step five's entire job is to figure out what function pointer should actually point to. This is the densest code in the entire presentation, so let's walk through it slowly. Look at box 1, the trigger. Inside the thunk store init function, it calls resolve barrier. Notice that the correct function back, once it gets the correct function back, it patches store function equals to function and overrides itself. Box 2, the resolve compression. First, we resolve that ambiguous compression flag. It checks the runtime if use compressed loop is passed or not. If it is true, it uses our decorator system to inject the correct decorator, which is internal runtime use compressed loop, and tag it into the bit mask. It has successfully lifted a runtime boolean into compile time template time. Box 3, which is the GC resolution. Now we resolve the GC. It switches on the runtime, which is on the barrier set kind return, which is on the barrier set kind enum. Look at that hashtag defined macro. It uses an X macro to generate a case statement for every single garbage collector compiled into the JVM. Don't try to read every line here, focus on the switch statement. We are using the preprocessor to generate a case for every GC. This looks ugly, but it bridges the gap between runtime values, which is the enum, and compile time types, the template class. It then requests a function pointer to that exact class's loop access barrier. Now, box 4 is domain routing. The final step before returning the pointer, the post runtime dispatch struct. Notice that it takes a type erased void star address, uses the decorator to calculate the exact heap type based on the runtime, and safely reinterpret cast it back to the complete C++ type. Finally, it uses a compile time check, whether it is in heap or not, to route the call to the final GC method. It returns this perfectly typed, perfectly optimized function pointer all the way to the box one, attaches it on a runtime, and our runtime bridge is complete. So step 5 just resolved an incredibly complex X mapping, rehydrated a type erased pointer, and handed a statically bound function pointer to the thumb. What exactly is that function pointer pointing to? It is a pointer to the GC barrier set access bar. The barrier set access barrier is the terminus of the entire pipeline. It is the C++ interface that connects the JVM execution engine to the active garbage collector. Look at the base implementation here. Two very important things are happening. First, look at the inheritance, the protected raw access barrier. It uses the raw access operation we looked at in the phase 2 as a private mixin. It completely hides those low level atomic operations from high level GC tracking logic. Second, look at the default behavior for a primitive store in heap. Because GCs generally don't care about integers, it simply delegates to raw store. It is a completely inline zero cost path. But most importantly, look at the template parameter, the barrier set T. This is the exact concrete C++ type, like G1 barrier set, that step 5 just resolved and handed to us. Hold on to that thought because that parameter is the secret to everything we are about to do. If we want different garbage characters to share a common tracking logic, we need inheritance. We need inheritance hierarchy. But we already established in the beginning that we won't be using virtual functions. So when C++ developers want polymorphism without tables, they usually reach for CRTP, the curiously recurring template pattern. As you can see in this standard textbook example, the base class accepts the derived class as a template class parameter and then uses static cast of derived star to this to call the derived class to call the derived classes methods. It guarantees inlineability. Why does hotspot need this? Because of aspect oriented programming. Generational GCs like serial, parallel, and G1 need to execute tracking code before and after you write a pointer to memory. So, hotspot provides an abstract skeleton called the mod_ref barrier set, which is modified reference. Look at the code on the right. We want a sandwich. We want to call the pre-write hook, do the raw memory write, and then call the post-write hook. Now, these hooks are stateful instance methods. That is, they need an object. But here is our C++ dilemma. The pipeline just called a static entry point. We do not have a GC object instance. We do not have a this pointer here. So how does mod_ref base class statically call the derived GC's hook? If we try to use standard C++ patterns, we hit a brick wall here. Let's look at attempt mode. The standard CRTP failed because, as we just established, we are inside a static method. There is no this pointer to cast. But now, what if we try a static layered CRT? What if we just called barrier set T colon hook, the static function, as a static function? That will fail too. Why? Because the actual GC implementation is highly stateful. The write_ref field hooks need to access the member variable of the GC object. So you see the paradox here. We are sitting inside a static entry point and we desperately need to invoke a stateful instance method on specific runtime configured garbage collector and without using vtable. So this is the hotspot solution. I call it decoupled CRTP. And I think it is an absolute masterpiece in C++ architecture. It separates the behavior, the static template hierarchy, from the state, which is the runtime GC instance. Look at the code for OOP store in here. First, we fetch the global runtime singleton, which is the global barrier set. There is a very subtle C++ trick here. The barrier set base class holds the runtime state, but it knows nothing about the templates or derived class. That is why we can store it as a simple static global singleton. However, the behavior lives inside the subclass access barrier, which is templated. So base class does not know anything about derived class, but the subclass access barrier knows about the derived class. So that's why we can have a static global variable in the base class. Now, because step 5 passes the barrier set T, which is the actual derived type of the active GC in the runtime, like for example, maybe G1 barrier set, we can take that generic stateful singleton and safely cast it. The barrier set cast, barrier set T, global BS. That's why static cast work here. Because we are doing a static cast with the exact derived type that is actually being used in the runtime. Otherwise, we don't know what will happen. The best thing that would happen would be a crash there. The payoff. We successfully merged type erased runtime state with compile time template behavior. We Please note that we use BS with arrow template right ref filled pre syntax to execute a statically bound dispatch directly to an instance method. So no vtable with perfect inlineability, and we have full access to the GC state. How do we ensure this doesn't penalize simple garbage collectors? By relying on the compiler's state code elimination. The base class defines these hooks as empty inline function. Because the oops store and heap sandwich we just looked at is 100% statically bound, the compiler evaluates it instantly. If a derived GC barrier set like serial GC does not shadow those hooks, the compiler binds to these empty base hooks and immediately strips them out of the binary. The abstraction costs to zero runtime CPU cycle. But what happens when GC does need to track the data? This is the ultimate payoff for the entire architecture. Let's look at one example of G1. G1 is a complex garbage collector. Its free barrier is very expensive. It has to save overwritten pointer to a queue. But if we are initializing a brand new object, that is, the old pointer is just garbage memory, tracking it is just a waste of time. If we look at the G1's implementation of writer filled pre, it checks a decorator bitmask. Has decorator is destination uninitialized. Remember that because the decorators are standard integral constant, this is evaluated entirely at compile time. If the C++ developer tagged this memory right as an uninitialized back, if the C++ developer tagged this memory as uninitialized back at the public API, the compiler completely deletes the enqueue field branch from the field machine code. There is no runtime branch prediction penalty. A massive complex GC state machine is completely erased at the compile time, leaving nothing behind but the raw access and the post loop. Now let's zoom out. Why did the OpenJDK team go through agonizing effort of building this deeply nested, macro-heavy template metaprogramming pipeline? Obviously, to decouple the JVM, but they also wanted to achieve a total modularity. This work was actually blocking introduction of ZGC, which was a new state-of-the-art garbage collector at that time. So by separating this abstract base classes, which are useful for fulfilling the GC contract, and providing specialized implementation like G1 and for ZGC, and using this lazy runtime setup paired with post runtime resolution with X macros and decoupled CRTP, we have successfully decoupled the JVM execution engine from garbage collectors. Today, if you want to introduce a brand new garbage collector for Java, you don't have to touch the rest of the runtime. You just write a new barrier set class, fulfill the contract of APIs, and plug it into the X macro, and the pipeline wires it perfectly. It is worth noting that this Access API was designed and built around C++14. The code we looked at today relies heavily on SFI NAE, standard enable if, and standard integral constraint. It is complex and verbose. If you were to build this same architecture again using using C++20, the syntax gets much more cleaner. The complex SFI NAE routing can be replaced with highly readable C++ concepts to constrain the templates. And the has decorator integral constants can be evaluated natively using if const expert, removing a lot of the template boilerplate. The architectural pattern still remains brilliant, but the modern C++ will make it significantly easier to read and maintain. Let's look at the architectural trade-offs. As architects, we know there are no silver bullets, there are only trade-offs. The pros: the architecture now creates a pit of success. By forcing the developer to use access OOP store, it is literally impossible to accidentally forget a GC barrier. The compiler would let you, and as we saw, it provides absolute uncompromising runtime performance with zero vtable and perfect with zero vtables and then perfect as we saw, it provides absolute uncompromising runtime performance with zero vtables. The cons: you pay for this at compile time. This massive template pipeline significantly increases the build times. Furthermore, the cognitive load requires to debug or extend this metaprogramming engine is incredibly high for new engineers joining the project. And what are the lessons? You won't need a JVM to use this. You can use these patterns in your database, game engine, or trading platform. So, what as C++ developers working on our own large systems learn from the JVM? Identifier. Identify your matrix of doom, the combinatorial complexity. Separate intent from implementation. Encode the configuration metadata into the type system like decorators rather than passing runtime boolean flags. Move everything you can to compile time. Use const expr and type traits to prune dead branches before the code ever reaches the runtime. Simplify. In the runtime, when you absolutely must cross the boundary between static compile time code and dynamic runtime state, use lazy thumbs and decoupled CRTP to preserve static devirtualization. Before we move to Q&A, if you are the kind of C++ developer who likes to read the actual code to see how this sausage is made, here are the resources you need. The entire OpenJDK code base is on GitHub. If you want to trace the exact template pipeline we looked at today, go straight to source hotspots share oops access.hpp. The engineers there have written absolute fantastic novel length comments in that header file explaining the architecture. I have also linked the official JEP 304 ticket, which explains the high level rules of the refactoring, and a link to the original 2017 mailing list thread. Reading that thread was fascinating for me. You get to see how world class JVM engineers debate the exact trade offs for this refactoring. The JVM is a masterpiece of C++ engineering, and the Access API is one of the most elegant subsystems. Thank you for diving into the depths of this hotspot metaprogramming with me today. I am Shubhankar Gambhir, and I would love to take your questions.